maybe I should not for this because I should not make fun of other professionals. I once made fun for some other professional, and you wouldn't believe what a teaching evaluation I got. It was like, wow. Someone got really upset with me. Anyway, I will not make fun of other professionals, only for our own. So, you can hear me now? Yeah. Okay, so then I went back home, and of course I Googled the rule of 72. And the whole idea of the rule of 72 is, of course, it's an approximation. No surprise. And the reason that it works, that if you have the component interest at any second, okay, at very, very small time, very, very small, then the correct number is 69.3 because it's log of 2, okay? And then since you don't get the interest every second, but you get it once a year in this example, then the number is a little bit more, okay? And why 72 is such a nice number? 72 is such a nice number because it has so many number that it's divided by, okay? So it's very easy to say, oh, if I have 8%, then it's very easy to do the calculation, okay? And then I looked up who was the first person who came up with the rule of 72, and that's completely shocked me. Would you guess who was the first person? Who was the person who invented the rule of 72? Jesus. That's even more impressive. Maybe Jesus knew it, because I don't know. I should look. Because I've been like many places, Jesus, because I'm from Israel. You know, I've been around many places. Jesus, I should look. But no, someone, maybe, you know, he's also kind of famous, but more modern. No, nothing. Someone, let me give you, someone who must be smart and really understand the power of approximation. Coming close. That's people at this level even a bit higher than him. Einstein, right. So actually it was Einstein. So Einstein is famous for relativity, the photoelectric effect, and the rule of 72. Okay. So it was actually Einstein. And then, I cannot not making fun of other. And then you go out to the internet, and then amazingly enough, after the rule of 72 that is not going after Einstein, there's the rule of, come with some 2 other names. And what these other rules of whatever, they add the second term in the expansion of log, okay? And it was like, you know, you don't understand what the idea of approximation. If you just want something very fast, you have leading order approximation. If you want the exact number, you know, it's a log. There's nothing to, you know, there's the exact solution. You know the exact solution, right? So that's the one thing that we as physicists, we know. If you have the exact solution, you either use the exact solution or you use whatever very rough approximation. But start having this. And then there's the rule of 70 and the rule of 71. So if the, right? So if I think it's something at 5%, the rule of 72 is exact, okay? So below, it's better to use 71, and above, it's better to use whatever, 73 or something like this. Okay, now everybody's here. Now, how many you think now? Estimate, the rule of 72. Where's Jeff? Jeff. He's my own student, and he's late. You will? No. He will really. He feels so bad about this. No. Because I mean, you come here early in the morning. You expect your student to be here, and listen to you. They are not here. Okay. Anyway, so what I did so far, I was basically talking about model building, either standard model, how we build the standard model, or going beyond the standard model. And today it's a kind of a whole different topic, and I want to discuss how we're actually going to do the measurements, how we measure all those flavor parameters, how we test all those nice pictures I was telling you. And in a way, it's a whole different approach to physics that we are using. When we do model building, it's really different than when we are thinking about making the measurements, okay? And the question I'm going to ask is, we discussed the CKM. So, for example, I want to ask you, how would you measure VCB, the absolute value of VCB? Okay? So I'm not saying how you measure it, how we get sensitivity, how we get processes that are sensitive to VCB, and how we can actually get them. So if we're talking about leptons, for example, how do we measure G fermion? G Fermi. How do we measure G Fermi with leptonic decays? You just take the muon decay, you calculate the branching ratio, and you know G Fermi directly from this, right? What is the big problem when we move to the quarks? The big problem with the quarks is the strong interaction. And the strong interaction is a problem. I hope you know why. Because it is strong. That's why it's called the strong interaction. And in physics, we already make these jokes. You remember we make these jokes about, you know, as a physicist, when you see a function, what you do to a function? You remember this? Right? You expand and truncate. Now, what happens when this function is not, there's no small parameter for the function? What do? You cannot expand. How you expand a function without a small parameter? Put it on a big computer, yes. So what I do usually, I go to the other side of the street, right? I just avoid it, right? But you're right. Some people are more, you know, courage, and they go and try to do something. For example, take it and put it on the grid, right? But that's the problem of QCD. The problem of QCD, of course, we are very interested in QCD for its own sake. But when you try to understand the weak interaction, in particular the flavor sector of the weak interaction, QCD is something that we have to work around it, somehow to solve the QCD, because QCD is what making us the issue. So the whole issue of this part of flavor physics, the part of flavor physics of how do we actually get sensitivity to the flavor parameters, the name of the game is always like this. How can we somehow get around QCD? Okay, so that's the name of the game. So that's what I'm going to discuss today. I'm going to do very brief, because I can talk about many more. I'm going to give you some example of how we how we go around QCD. Okay, so let me give you the first example. So the first example would be a VCB. So how would you expect to go for VCB? For example, I want to look for the decay. We're going to see mu neutrino. Why this decay is sensitive to VCB? Let's write the Feynman diagram. The Feynman diagram will be BC, muon and neutrino. And here I have VCB enter in this vertex, right? Because it's the U2C. So then you can do the calculation, and everybody know to do 3-level, 3-body decay. So when you do this, you find that the width is proportional to MB to some power. Anybody remember the power? 5, very good. MB to the 5 times VCB absolute value squared. Do you see why it's absolute value squared? Because this is the amplitude, I just squared it, times some phase space that must go like MC over MB. That's some phase space function that we actually know it, okay? Just don't bother to write it down, okay? So all of this looks very good, but what is the problem? What is the real problem when I'm talking about this? If you just look, what? Sorry? So one big problem is that I cannot really have a B quark decay. What I have is a B meson that decay, or a B hadron in general. So the question is, this is something very nice because it's really easy to calculate. It's really easy, okay? But how this is actually related to what I measure in nature, which is the B meson. And there's actually another problem here, and that's the problem of the mass of the B quark, right? What I really know well is the mass of the B meson. And actually, by now, we all know it, right? But I don't know very well the mass of the B quark. Actually, it's really hard. How do we define a mass of a quark that is not physical? It's never free. So what do I mean by a mass? So the way when we do, the way we think about it when we do model building, we say we don't care. There's just a parameter in the Lagrangian. And as long as this is a parameter in the Lagrangian, I really don't care. But when I do the calculation, this parameter in the Lagrangian start become a physical mass that decide my phase space, then I do care what its value and exactly how I define it. So when we have a parameter in the Lagrangian, we know the story that I said, oh, I don't care. I can use whatever renormalization scale I want or regularization scale I want. As long as I'm consistent, I'm fine, right? But when it's become a physical mass that demands phase space, I cannot use whatever I want. I have to be much more rigorous, okay? So now we see where the problem is. Okay? So I'm going to discuss this to some details. This one example. Of course, there's many other decay, but that was like, you know, to start it off. So how do we deal with QCD? So how do we deal with QCD? How to deal with QCD. So we already heard one solution, and that's to put it on the grid, or try to say it in other words. One way to solve QCD is actually to try to solve QCD, okay? It's to get around, instead of getting around, let's say, we have a problem, let's solve it. I know most of the time we don't do it, right? In everyday life, we don't solve our problem. We find way around them. But let's say, solve it. Solve I gotta solve QCD. And actually, the only thing that we have right now to solve QCD is the lattice. So the lattice is the only rigorous way to solve QCD. And the lattice, I'm going to describe a few things that we can do with the lattice in a minute, but it's still limited. I mean, we're still not hoping that lattice will solve the world. So the stories I heard, so the person who invented the whole idea of lattice is Wilson, the same one from the renormalization group equation and everything. And he done it when he was at Cornell in the 70s. And our old professors are telling me that when Wilson started it, everybody around was sure that, within half a year, we'll just solve QCD, okay? Said, we just need a little bigger computer and we'll just solve QCD, okay? And when times go on, the time from the development, it's like half a year after the discovery of lattice QCD, they say in half a year we're going to solve it. 1 year after the discovery, they say in 1 year. 40 years after the discovery, they say 40 years, okay? So there's something like this, right? So we don't know when we will solve QCD, but we definitely made, people, not me, I was never work on lattice, made some impressive progress, I will say. The number 2 tools that we have, and that's probably the one that we use the most, is to use approximate symmetries of QCD. The approximate symmetries of QCD. And you probably heard some of the approximate symmetries of QCD. When I say approximate symmetries of QCD, what comes to mind? Someone? Sorry? Chiral perturbation theory. So I hope, at least I'm sure some of you learned some idea of chiral perturbation theory. There's other approximate symmetries of QCD and how they are related to this. I will discuss it in a minute. What I'm really looking for the approximate symmetry of QCD is either at very low energy. So at very low energy, actually, E over lambda is much smaller than 1. That's for very low energy. And when I have actually high energy processes, I can actually use that lambda over E is much, much smaller than 1. So in the region where the energy that I have in my process is either much smaller than lambda QCD or much larger than lambda QCD, there's some extra symmetries of the QCD interaction, and we can actually exploit those symmetries. And the number 3 is to completely go around QCD. That is, there are some analyses, and they are not generic. Each one of them have its own little trick that you can actually do things like so you will never have to calculate anything and actually measure all the QCD that you need. Okay? So that's, I would say, it just measure it. So it's not always easy, because usually I said I need the QCD input in order to get the weak interaction. However, in some cases, we can actually measure, and with a very, very mild assumption, we can actually measure all the QCD that we need. Okay? So basically, these are the 3 tricks that we are using, or the 3 tools that we are using, and we see what we can do with them. Okay? So the idea of ADS QCD is fall into this, number 1, with the hope to actually eventually solve QCD. At this stage, the ADS QCD is still so far behind the lattice, and I don't think, as of now, people get really excited when they get things within the thing that we already know within 10%. So we are definitely far beyond. Nobody claimed that they can make actually something that nobody else knows how to do. But maybe eventually, yes. Yes, so use of ratio is basically how you do measure it. It's how you go around. Okay, so I will discuss some ideas where you actually, instead of you cancel the QCD. So measure it or go around it. That's what I mean by this. Okay, so So you're somehow smart enough such that the QCD cancel in your calculation, and you never need to actually determine it. And many times you either measure it or you cancel it. Okay? So these are the things. Okay? So let me start with the number one, with how we try to actually solve QCD and what do I mean by this. So let's talk about the example that I give here, the semi-leptonic B decay. And let's say what we really have is something like this. Let's say we have B going to L muon neutrino, or a general lepton. So what we have a meson B decaying to a meson D. And then we say that, oh, our intuition that this process is done by the following Feynman diagram. Okay? So what is really the problem here? Okay? So let me remind you your very basic quantum field theory. So remember when we did quantum field theory and we defined a fermionic field. Let's say a fermionic field that I call B. What is the fermionic field B? Okay? A fermionic field B is something like, that's really a bad name because we use the B and B dagger for creation and annihilation operator, okay? But, so this one, it's basically made out of, let's don't call it B, let's call it psi. Psi, you can do it like a B plus a B dagger. And what a B is doing for us, a B annihilate a B quark, and a B dagger create a B, an anti-B, right? And what was some of the basic assumptions that we did when we were doing it? We assume, oh, what this field does, it creates a free B quark, okay? The very basic idea of perturbative quantum field theory is that your zero-order fields are just free fields. You remember this? Yes? It was really second lecture in quantum field theory, right? And now what I need to do, I need to create a B quark or annihilate a B quark that is not a free B quark, okay? That's the big problem. The big problem is that my operator, all I know, when I do quantum field theory, all I know is to create and annihilate free quarks. And then we use perturbation theory to discuss higher order things. Here I cannot use it because the B that I create is a bounded B that is bound within the quark. Okay? That's the big problem. But we cannot really use our understanding of. So how we are actually parameterize our ignorance. Okay, that's always a nice thing to do. You parameterize your ignorance, and then it's very clear what you try to do. So the way we parameterize our ignorance is by saying what we really want. We want something like this. We want the matrix element of the following hadronic things, right? So what I have the matrix element between a field that can annihilate a B, a field that can create a charm, but not between the vacuum, like we have in quantum field theory, but within some bound states. Okay? In quantum field theory, when I have just B dagger C, you know Feynman diagrams. When you have a B, what does it give you? Basically give you whatever, some U with some spinors. The gamma mu? Sorry. Yeah, because it's a vectorial current. But we can actually, any Dirac structure can be there. Okay? So that's how we say we've parameterized our ignorance by saying what we really need from QCD is to calculate this kind of matrix element. What we need is how we put our free field operator and we sandwich them between some mesonic state. And we just don't know how to do it from perturbation theory. That's a non-perturbative thing. Okay? So how we do it in the lattice? So for example, the way lattice calculate this matrix element for us is with the following idea. You discretize your space-time, then you actually really calculate the action in a discrete limit. And ideally, you take the lattice distance to 0. And ideally, once you take the lattice distance to 0, you recover the continuum limit. Okay? That's the simple idea. Yes. That's right.
So how is that justified from
Oh, so why I will discuss it soon. Okay, I will discuss when we discuss the approximate symmetries. I will discuss why I can forget about the light quark that's going on. What I really want is, if I say when I try to do it on the lattice, I don't neglect anything, right? Because on the lattice, I don't have the light quark operator. The operator doesn't involve the light quarks. right? The operator is just this, right? But the B meson is whatever it is. And I just remind you that it's only this quark model picture of a B meson that is made of a B and a U or a B and a D, right? The B meson is a much more complicated object. We cannot think about the B meson as, a B quark and a U quark coming together. It's not like a hydrogen atom. So when you do it on the lattice, that's the real B meson of the full QCD. And the approximation is the lattice spaces. So if you like, the lattice try to exactly solve QCD, but there is an expansion parameter, and the expansion parameter is the lattice spaces, some A squared, etc., where when you take A goes to 0, you get the exact result. In practice, we are, a little bit far from there, but there's very, very impressive results so far, okay, in some cases. As far as I know, from my lattice friends, if you have a matrix element that you have only one meson, like a pion go to the vacuum, and when you have just two mesons like this, you can make a lot of progress. When you have three of them, like B going to K pi, the lattice is still completely, yes? Okay, Tom is, it's hard. So what my friends tell me, yes, don't count on us on B to K pi in the near future. Yes? Yeah. But on these kind of things, actually the lattice made a lot of progress. And basically the lattice just calculate QCD from first principle. So you take the lattice output, and once you have the lattice output for this ignorance, you can plug it into the measurements, and you can get VCB. Okay? Good? Okay, so let me move on to the second point, and I want to discuss the approximate symmetries of QCD. And as I said, this is the one that I feel we use the most. And the idea is either we use low energy, and we use things like chiral perturbation theory. What chiral perturbation theory basically is doing for us? Chiral perturbation theory basically tells us that at low energy, our degrees of freedom are pions and maybe kaons. And we use pion and kaons as our fundamental degree of freedom. And it's an effective field theory that is valid up to the scale of lambda QCD. And we have and the expansion parameter is P over lambda. Okay? And we have, just like any other effective field theory, you work up to some scale, then you introduce a finite number of unknown parameter, you measure those finite number of unknown parameters, and then you can start making prediction. Okay? And then in principle you can, yes? Oh, yeah, of course. There's like so much more to do. Okay? And I'm really going to give you like so little today. I'm just going to touch on ideas, okay? And actually for the phase of VCB, the phase itself is not physical. What is physical is relative phases, and hopefully I will get to this. Okay, so bear with me. I'm just trying to get the idea how we use this kind of things in order to get sensitivity. And the point is that unlike other things, basically for any measurements, you have to invent its own tools. It's not like Feynman diagrams. So when you have perturbative quantum field theory, all you need is one tool. It's called Feynman diagrams, and then you can calculate in principle anything, right? It's this one tool that we use for here. There's not something like this. Basically, any process, you need its own tools. Some tools can work for 2 or 3 cases, but there's not like a universal tool that works for everything. Okay, so that's about chiral Lagrangian and chiral perturbation theory. I will not talk about it just because I want to cover other things. I hope some of you learn something about it. I want to talk more about the other limit, the limit of the heavy quark, which usually people are not touched upon it in a standard, whatever, QFT or QFT2. How many of you learn heavy quark symmetry in your QFT classes? 1. Okay. 1.5. Okay. Yeah, so it's less. So I want to discuss it a little bit more here about things. Okay. So what is the idea? What is the idea of heavy quark symmetry? The idea of heavy quark symmetry is the following: that I'm using the fact that my heavy quark is much heavier than lambda QCD. Okay. So in particular, I want to think about this example that I keep thinking about is B going to C. So what I have, lambda QCD is of order a few hundred MeV, and the mass of the B is whatever 5 GeV. So it's a value factor of 10 more than lambda QCD. So the energy scale that I have when I have a BDK is much larger than lambda QCD. And in this limit, we can take the limit that the heavy quark go to infinity. And when the mass of the heavy quark goes to infinity, QCD, there's two emergent symmetries of QCD. Okay? The symmetry of QCD that are suppressed by 1 over m in the real world, but in the limit that m goes to infinity, there are two extra symmetries. So let me describe these two extra symmetries. So I'm described heavy quark symmetry, and I want to discuss the two extra symmetries that QCD gains when we take the mass to infinity. So I want to take the mass of both the charm and the bottom to infinity, but keep the ratio finite. Okay? So the ratio is about 1 over 3, but I take both to infinity. So the first symmetry is what we call the flavor symmetry. The flavor symmetry, which is B to C flavor symmetry. And the idea is as following. If you take the mass of the B and the C both to infinity, and now you have a meson, and I change in my meson, I change the B quark into a C quark, what would happen to the meson? The answer is nothing. Okay? And the intuition should come from you basically from chemistry. In chemistry, when you take your whatever atom that you have, and you take an isotope of it, the chemistry doesn't change, right? Why we don't care if in our body if we have a carbon 12 or carbon 13? It's a big difference, right? Suddenly it's a whole different material. Why we don't care? Because of the heavy quark symmetry of chemistry. Okay? That's what it is. Because when we talk about the light degrees of freedom, chemistry only care about the light degrees of freedom, right? So I don't really care if the nucleus is 12 atomic unit or 13 atomic unit. To all practical purpose is infinite, and therefore I don't care about it. The same happens here. If all I care about is what's happened to the QCD, all this non-perturbative QCD, if the heavy quark goes to infinity, all I can think about this heavy quark is just a source of color charge. Okay? And that's what's really bound the light degrees of freedom into the things. So I really don't care if my heavy degree of freedom, how heavy it is. As long as it's heavy enough, I don't care what it is. Okay? So the flavor symmetry is just that you can actually don't care when the B goes into a C. Good? Maybe you can guess the second symmetry just because I was telling you that it's like chemistry.
What about quantum numbers? They are quantum numbers that are very different. Even if I take that as a background.
Very, 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 very important. We talk about QCD. In QCD, is the B and the C have different quantum number? No. So you are completely correct that the flavor symmetry of heavy quark symmetry is broken by 1 over m effect and by QED, right? And by the weak interaction, right? So this is a symmetry of pure QCD in the limit of heavy quark. So you're completely correct that you have other breaking. Good. So now what is the second symmetry that you can think about? So I give you a hint. The hint is as following. We talked about chemistry. Now we can actually make it simpler. Let's think about the hydrogen atom. Hydrogen atom is physics, right? It's not chemistry. No. So I don't care now about the light quark. What I'm just saying is that there's a symmetry in the there's some fundamental symmetry of QCD that when I take the heavy quark to infinity. Sorry? Yeah. So that's the picture that we have. We have the picture that in the heavy quark limit, the meson is like a hydrogen atom. We have a very heavy thing sitting in the middle and light quark going around. So the heavy quark in the... Okay, come back to hydrogen atom. It's really, really cool. Hydrogen atom, there's so much to them. What is the extra symmetry that we gain when we take the mass of the proton to infinity? Yes. Right? Is the hyperfine splitting goes to 0, right? Because the mass of the proton is finite, we have a very, very small splitting in the ground state. You remember that, the hyperfine splitting? It's very famous. What is this famous transition? What is the wavelength? The 21 centimeter, right? It's scale like 1 over the mass of the heavy guy. Okay? If the mass of the proton was infinite, the two hyperfine splitting will degenerate and we gain an extra symmetry. Okay? We will get the same symmetry here. If the mass of the heavy quark goes to infinity, we gain this extra symmetry that we call the spin symmetry. Right? So we don't really care about spin up and spin down, or in particular, we don't care about this versus this configuration. Okay? And Actually, this one, the spin symmetry of heavy quark, it's something that we can see from the data. It's kind of cool just looking for the data. Probably I should have write it up this in the beginning of the lecture. So let me give you the following things. The mass of the B star minus the mass of the B is about 46 MeV. The mass of the D star minus the mass of the D is about 140 MeV. And the mass of the K star minus the mass of the K is about 400 MeV. Okay? Now let me remind you what is a B star and a B in the quark model. So a B meson is made out of a heavy B and a light, say, U quark, okay? And just like in the hydrogen atom, we can combine them into a spin 0 and a spin 1. It's the J equals 0 and J equals 1 of the hyperfine of the ground state. Okay? So the B meson is the spin 0 combination, and the B star is the spin 1 combination of the two spin. Okay? And remember, in the hydrogen atom, all we care about is the fact that we have spins. We don't really care about the fact that we have electromagnetic interaction. So here's the same story. QCD is much more complicated than QED, but all we care about is just the fact that in our model, all we have is to combine two spins. Okay? So what can you get from this kind of numbers? Okay, what do you see? Again, you see some pattern, right? What's the pattern that you see? That yeah, so the heavier the quark here, the splitting is smaller. Does it make any sense? Just recall the hyperfine splitting. How the hyperfine splitting scale? It scale like ME over MP. Or in general, it scale like 1 over the mass of the heavy guy. Okay? And look how nice it is, right? Going from B to D is about a factor of 3, and going from D to K is about a factor of 3. You know, what is the mass of the B? We all know. 5 to 80, we all know. What's the mass of the D? 1865, roughly. What's the mass of the K? 493. Okay, so that's about 500, that's about 1800, that's about 552. So it's about a factor of 3 going from here to here, and we see that the splitting grow by about a factor of 3. Okay? So this 1 over m, you just see it from the data. And we understand it from fundamental Qcd. Okay? It's basically just the hyperfine interaction of this kind of thing. Very good. So we actually understand that we have an approximate symmetry of Qcd. And these approximate symmetry of Qcd are broken by 1 over m effect and, for example, by a QED. So how can we use these approximate symmetries in order to gain some, for example, to measure VCB? How do we use this? And we can do it in 2 ways. I'm going to describe one way in details, and the other way I will be very, very quick. So the first way to do it is to use our big assumption of QCD. And this big working assumption of QCD go under the name of the quark-hadron duality. Okay. Kind of interesting that not only string theorists have dualities, we also have dualities, right? So this is the quark-hadron duality. And what quark-hadron duality is telling us? Have you heard about this quark-hadron duality before? So what quark-hadron duality basically tells us? It tells us, we do measurement in terms of hadrons, and we do calculation in terms of quarks, and we can still talk to each other, right? As a theorist, we like quarks, experimentalists like hadrons, and we can still be friends. Why we can still be friends? Because we have this duality. So you can do calculation in terms of quarks, and you can do measurement in terms of hadrons, and you can talk to each other. What is the fundamental principle of this quark-hadron duality? Which we cannot really prove, okay? But there's quite a lot of proofs around it. I don't think there's a formal, absolute proof of this concept. The big concepts of quark-hadron duality is the fact that you need to make an integration of a large enough phase space of hadrons, okay? So if you look at one point in phase space and you do things in terms of hadrons, you say, I have no idea how to calculate it in terms of quarks. However, if I make large enough integration of a large enough region of phase space in terms of hadrons, the result agree with my calculation in terms of quarks, okay? And when I said large enough integration, what is large enough? In Q squared. Large enough, much larger than lambda QCD. Okay? Lambda QCD set the energy scales. So if I can do integration of scales much larger than lambda QCD, then I'm fine. And by much larger, what do I mean? Usually much larger is 2. Okay? It's good enough, which is kind of surprising. Right? Sometimes even order 300 or 400 MeV, it's good enough. But ideally, you want to go for like 1 GeV, 2 GeV integration, which is much larger than QCD, and then we can actually trust this quark-hadron duality. And the most famous example of the quark-hadron duality is the R. You remember the ratio R? R, which is sigma of E plus E minus going to hadrons over sigma of E plus E minus going to mu plus mu minus. Okay? And I think in almost all books on the standard model, it's appearing in chapter 1, and you saw this plot many times, right? So you look at R as a function of some energy scale of this, and it starts at 2. When you have only 3 light quarks, it starts at 2, and then at some point it becomes 10^3, and then at some point it becomes 11^3, and that's when the jump kicked in, and that's when the bottom kicks in. And when you look at the data is clearly, so that's kind of what the quark calculation predicts. And the data is something like this. Okay? And when you integrate, you get this kind of things. And why the data is floating all over the place? Because we have resonances, and the resonances kind of take away from the side. So as long as we integrate of big enough phase space, we can actually use the quark calculation. Okay?
So you're saying you can integrate out phase space, but how do you get R?
R is a measurement. So what you measure the cross-section of E plus E minus 2 hadrons as a function of S. So you set the center of mass energy, and at each point of S, you have a different cross-section. And the cross-section for the hadrons varies very dramatically, right? So if you sit on the psi, the cross-section is more than 100 times more than the average. So the psi is actually somewhere up there. Okay, E plus E minus going to psi, to a CC bar resonance, is so much bigger than the average. Okay, but as long as you integrate it overall, your quark calculation agree with what you measure with hadrons. Okay, it's really important. You measure hadrons, and you have to integrate, and that's the important part. The important part is the integration of a phase space. Okay, when you integrate over phase space, then you get it. And the intuition, I hope the intuition is clear. At the low energy, what we produce a quark, and then the quarks hadronize. And all this hadronization give a lot of interesting effect, but they are always at the scale of lambda QCD. So if I integrate over things that are much bigger than lambda QCD, I don't care about it, because I create a quark, and I can still think about it at quark until I hit lambda QCD. And only after I hit lambda QCD, the things become things that I cannot really calculate. But if I integrate, I kind of go back, and I really can think about it as quarks. Make sense? Yes? Kinda. Oh, yeah. So indeed, I will talk about phase space in a minute. What I really care about, that I integrate over some energy scale. Okay, so in this case, I have a measurement at each given point, and then I have to integrate over these things. Okay, and in phase space, again, I can think about any point in phase space as one measurement, and I integrate over it. And that's what I'm going to use now. The important point is that I make a measurement at I have many different energy scales, and I integrate over some energy scale. Okay, and here the energy scale that I integrate is the simple one. It's just S. It's just the center of mass energy of the collider. Make sense? The RGE is only about the calculation. All I'm saying is the following. The statement is the following. We do the calculation in terms of quarks as precise as you want, and we do the measurement at hadrons as precise as your friends can do it, right? And then you say, as long as I integrate long enough, big enough areas, I get higher precision. Okay? So now how can we use it for things like B going to CLNE? The way we use it for B going to CLNE is, instead of integrating over the center of mass of the decay, the B meson itself provides us with many center of masses, right? Because what is the energy of the C quark? So what I'm doing is the following. I'll come back to the example that we have. And in the example that we have, on its class B going to X sub C, muon and neutrino. So what I have is the following. I have a B meson decaying to some quarks that involves a C. It can be a D star, a D pi, D and 2 pi, D and 3 pi, D and S and 2 kaons, etc. There's many, many hadrons that I call X sub C. It's all the hadrons that the B quark decay to, and the muon and the neutrino. The big point is that because I have a phase space here, the energy of the muon give me different energy of my hadronic system, right? So what I have, I can measure, say as the function of the energy of the muon, I can measure this branching ratio, or the width. So I will get whatever, some kind of a curve, okay? And this curve, in principle, will not be smooth because I can have some resonances here, right? So I will, my curve will go like this, depend on the resonance that I have. In terms of quarks, when I do the calculation, the quarks give me the smooth curve, okay? And the quark-hadron duality tells me that if I integrate on large enough region in the energy of the muon, I should get the same result. That makes sense? It's just the same idea of what we do there. So actually, we can formulate this in a more precisely. And what we do, we can actually formally show that we can perform an operator product expansion, an OP. And when we produce the OP, what we can show is that lambda of B going to X sub C mu ni is equal to lambda of B going to C mu ni times 1 plus A over lambda squared plus B, let's call it A2 plus A3 over lambda cube plus. So we can actually have a formal expansion in powers of 1 over, sorry, what a mistake. Plus A2 lambda squared over MB squared plus A3 lambda cube over MB cube, etc. So we have a formal expansion, and the expansion is given by lambda over MB. And those coefficients, A2 and A3, there's not only one coefficient, there are a few coefficients at each order, are just like in any effective field theory. If I truncate my thing here, I will end up with 2 new coefficients to first order this new coefficient that I have to measure. And after I measure them, I have what I have, okay? And in the limit that MB goes to infinity, these two results actually formally agrees, okay? Sorry? So why there's no linear term? That's a very interesting result. It's called the Look Theorem, because Look was the first person who proved it. And you actually find it in many other examples in hadronic physics that somehow the first term vanish. I still don't have a very good intuition why it is. Okay? I'm just saying that this is not the first example. There's also, I forgot about in kaon physics, there's another case that you start from second order. Okay? And actually, I should, we see quite a lot of places that the first term vanish, and I just don't have the intuition. I still hope to get this intuition one day, but just don't get it. But it's a very, very good for us, because it's second order, then the corrections are really small. If you had to worry about first order correction, your situation would be worse. Since you have to start in second order, you are better off. Exactly 0 in this expansion, right? You make an expansion and you calculate the coefficient. Yeah. So in this expansion, no, because here in this expansion, what's happening is that you think about the charm as part of the hadronic system, and the important thing is that we integrate. So the important of this is how good is our integration, and there's some correction that we say the breaking of the OPE. So there's some unknown breaking of this quark-hadron duality that we don't know how it is. However, we think that it's much smaller than what we have here. Okay? So in this case, we don't have 1 over MC correction. All the correction is 1 over mb. Okay? And think about the C as just part of your hadronic system. Okay? Good. So yes. So this lambda is roughly lambda QCD, okay? And you can choose whatever lambda you want, and that will affect your A2. And for example, let's just stick. I want to discuss now the case that I only stick for second order, and I'm going to discuss it, and maybe we can come back to a question after that. So let's stick ourselves to A2 only. And when you do A2, you find that there's 2 hadronic matrix elements that you have to calculate, and you can actually write them down, and in principle you can calculate them on the lattice, but they have a very clear physical intuition. Okay, so what I was telling you that in the limit that the mass of the B goes to infinity, all this is negligible, and I can do the Quark calculation is equal to the Meson calculation. However, the mass of the B is not infinite, so I need correction, and this is the first correction. And I told you there are 2 sources of this correction. And I'm not going to tell you what they are. I want first of you to discuss, to think. Can you think about the physical meaning of what correction I should have? What kind of correction I should have because the mass of the B is finite? Get your intuition from the hydrogen atom. Just think about the hydrogen atom. Think about beta decay. Okay, in beta decay, to leading order, we can forget about all the light degrees of freedom. I just think about, whatever, my carbon 14 decaying to nitrogen 14, and I don't care about the electrons. But there are corrections. What are the corrections that you can think about it? So it's not the spin orbit, it's the spin-spin interaction, right? It's this, It's the spin orbit is only the light degrees of freedom. It's the hyperfine splitting. So one correction has to do with the spin, right? So one correction is the spin. It has to do with the fact that the spin of the B is actually, there is some probability of the spin of the B to scale like 1 over B. And it's end up 1 over mb squared. And another one? Recoil, very nice. So the other one is the fact that actually the B, inside the B meson, the B quark is not at rest, right? The B quark actually is kind of moving, they have some kinetic energy. And this one is actually, so the other one is the kinetic energy, Kinetic energy of the B. It's the fact that the B has some kinetic energy inside the meson, and therefore when we decay, it's not decay at rest. And what is really cool that this one you can actually calculate completely just from completely classical argument of time dilation. You calculate, you say, oh, I know it's some wave function. I know the mass of the B. So since I know the mass of the B, and I know the mass of the B meson, and I know the mass of the B quarks, I know the average kinetic energy of the B meson, of the B quark inside the B meson. So it's just pure time dilation from relativity. And you do it very, very formal like this, and then you do it in this semi-classical hand wave argument, and you get the same result. Of course, you should not expect the semi-classical to work, but it's one example where the semi-classical argument actually works. So we actually understand what we are doing. We understand that we take, because the B is heavy, we can treat the B meson decay into a system of quarks using quark-hadron duality just as a measurement of my quarks, and I know how to calculate correction, and I understand the physics of those corrections, and we can actually get some control over QCD. What we really use here is the approximate symmetries of QCD. We use the heavy quark approximate symmetry of QCD in order to get intuition about VCB. Okay? So we measure this, and by measuring this, I can actually get some handle of VCB. Okay? And to give you an order of magnitude, we are talking about, right now, the state of the art is about 3% theoretical error. Okay? So this higher order correction that we don't really know, and are worried about violation of quark-hadron duality, we estimate the theoretical error at the level of 3%. Okay? We hope to do better, but as of now, it's not like in a standard perturbative QED that you just go to higher order, okay? Here, going to higher order not always solve the problem because you just produce more and more matrix element that you don't know how to measure, okay? Good. So there's quite a lot more to this that I just don't have time to discuss. Instead of using B going to XC, I can actually use B going to D, and use fully exclusive measurements and use the same heavy quark symmetry on B2D. And it's come under the things like the Isgour's-Y function. I don't know if you heard about it, but if you're not, you should. So I'm saying you. It's called the Isgour's-Y function. It goes after Isgour and Wise, who was the first people who realized that you have this function. And this function is actually tell you something about this hadronic matrix element, this one, that we cannot really calculate from first principle, but we know some symmetry properties of this hadronic matrix element, and using some properties of this hadronic matrix element, we can actually also get this VCB from exclusive decays. So that's called inclusive determination, because I don't determine the quark, the charm, and the exclusive one will be B2D or B2D star, and I can do similar tricks there. Not similar, but other tricks that use the same approximate symmetries. Okay, so that's basically all I wanted to say about this. Yes? Yes. Oh, so actually, here you just need to know what the mass of the B, and there's one of the 3% uncertainty that I was discussing, is what really you should use. And people discuss it to death, and there's something called, I forgot the name. Well, anyway, there's a fundamental limitation of how good we can actually do it. Okay? So we assume you can use whatever. You can use MS bar, you can use the pole mass, you can use the upsilon mass. There's many descriptions. And as long as you are consistent, you're in principle okay. So what you do, for example, in the upsilon description, you measure the mass of the upsilon 1s. The upsilon is the BB bar bound state. So you measure the upsilon 1s, you divide by 2, and that's how you define your MB. And then you actually start calculate a radiative correction, which are perturbative correction that you can do in perturbative QCD, and you calculate correction. Okay? And then you can do it with MS bar, and you calculate correction. So the correction are different. Right? So the one loop correction that you depend on your prescription give a different numerical value. So you said, oh, that's really nice. I can go to as much higher order that I want. But it's the same story with the fact that you know that any Feynman Feynman diagrams are not convergent, right? They are what we call asymptotic things, right? That is, eventually you get, when we in QED, when we go to 137 loops, we start diverge. Right? In QCD, it happened much earlier, right? And the uncertainty, you have fundamental uncertainty that's end up of this order of few percent. Okay? Because it's the alpha strong is much bigger than alpha weak. For both. And it's, so I was actually a little misleading. The Look Theorem is for the exclusive. The Look Theorem is not for the inclusive. So the inclusive, I don't think there's a name associated with this one. Okay, but actually it's happening in both. Okay, and that's really important because then you can actually get some. Okay, so let me move on, and I want to start some other things. It really took much longer than I was anticipating, so I'm definitely not going to get as far as I wanted to. But that's okay. The next thing I want to start is discussing meson mixing. And one of the biggest things about meson mixing that is important that unfortunately I will not have time to cover is how they are related to CP violation. But I want to discuss the formalism of meson mixing. And naively, we know it's a very simple process, right? What you have, you start, for example, with a B meson, and the B meson can oscillate into a B bar. Why it can oscillate into a B bar? Because it's a flavor change in neutral current process. And the theory of oscillation is something, it's called Rabi oscillation for, people knew it 8 years ago. When you produce a state that is not an energy eigenstate or mass eigenstate, it's oscillate. Why it's oscillate? Because it's only a two-level system. When you have a many body system, it's not oscillation. We start calling it a decay. When it's only a two-body system, then we have oscillation. With a three, it's okay. When we have infinite number of states, it's not oscillation, it's decay. That's the Fermi golden rule. The Fermi golden rule is oscillation in the limit of n bodies, right? That's what's happening. In a two-body is this. If you like, it's like the two slit experiments and the wide slit experiment. In wide slit, you have like this. In the two slit, you get the oscillation. Okay. So now the question is why we can actually, what kind of meson we can do, how do we measure it, and how we actually treat it theoretically. So there's four mesons that we can think about whether they oscillate. And the four mesons are the k-on, which is the SD bar, the D, which is the CU bar, the B, which is the, and the B sub S, which is, okay. Why there's no other systems? I said there's only four meson systems that I care about oscillation. Why there's no other systems? Can you think about other systems? Like why the pion? Why I don't include pions? Why? Why I don't include pion? Why pion? I don't talk about pion oscillation. Only about k-on, D, B, and B sub S. Let's start with simple. Why I don't talk about top oscillation? Why there's no top oscillation? Because top doesn't have a mesons. Let's take this statement as given. I mean, in principle, the top could create it, but it decays so fast that I don't care about it. Why we don't have pion oscillation? Because it's the same, right? In order to have oscillation, you need that the two flavors are different. Okay? So in principle, since we have only... Why we don't have charge B plus oscillate? Charge conservation. So I need them to be neutral and have a different flavor structure. Okay? And why I don't have things like K star bar oscillation? So I can have K bar oscillation, right? So the K can oscillate into a K bar. So also the K star should oscillate into a K star bar. Why I don't have K star bar oscillation? It decays too fast, right? So the time scales. K star decays strongly, so it's decay much, much faster than the K-on. So of course I do have oscillation, but they're completely irrelevant because of time scales. Okay? Very good. So we have only these four mesons that can oscillate. And in order to get the formalism of meson oscillation, we really need to think about how we treat time evolution. Okay? And that's something that we usually don't care about. When we do quantum field theory, we don't care about time evolution, right? We already did everything. We just calculate the matrix element and square it and say this is our decay, right? But now we have to deal with time oscillation, and then we do these things that yesterday Ofri was asking me, like, why you are doing it? So here, why I'm doing it. When you treat with time, what you have to do? You have to go to Hamiltonians, right? You remember this? You remember? Why do we introduce the Hamiltonian? Because we didn't know how to go forward in time. So we said, let's introduce Hamiltonians, and Hamiltonian will take you forward in time. Right? That's the role of Hamiltonians. Hamiltonians is the operator that moves you forward in time. Right? Which is very different than Lagrangian. Lagrangian are kind of treat x and t completely the same, while Hamiltonian treat time very differently than x. Hamiltonian really take you forward in time. So you have to use some Hamiltonian formalism in order to treat time evolution of our system and see how things oscillate. Okay? So basically what we have to do is the following. Let's assume that I produce a B, and at time t equals 0, my state, I call my state B of t. I say that time, that's my state. I produce a state B, and this B is a superposition of B and a B bar. And I assume that at t equals 0, the state B at t equals 0 is equal to B. Okay? And then what is this? So if I start, then B of t is some superposition of B plus a B bar, right? That's the idea of oscillation. You start with, say, a pure B meson, and then it's oscillated such that I have a B and a B bar, and I normalize my state such that A squared plus B squared is equal to 1. Okay? And it's changed with time. And you all know what the answer is, right? What it can be. Okay, since it's oscillate, what it must be a cosine. Well, it can be a sine also, but it's the same, right? It must be a cosine. And what should be the period of the oscillation? Just from dimensional analysis. Must be the delta. Well, it must have dimension of energy. So it must be delta E. of the two states, right? That's the whole, I mean, just really, really very, very basic quantum mechanics. When you have a two-state system, the oscillation must be delta E, because it's, or delta E over 2 or something like this, but it must be delta E, okay? And in the rest frame, delta E become delta M, and T become tau, the self-time, okay? And if you know in neutrinos, so I'm just saying without doing any calculation, just from our very, very basic understanding of NDA quantum mechanics, we know that the oscillation must be delta M times T. And do you remember what happened when you do neutrino oscillation? What is the oscillation for neutrinos? I'm sure you've seen it before. What is the formula for neutrino oscillation? Delta M squared time over 2E times T. Okay? So why it's different? What's the difference between those two? Why it's not the same? All I was telling you is basic quantum mechanics. You have two-level system. The oscillation is a sign, and that's the period. Why it's not the same in neutrino and in B physics? Relativistics, okay? Basically, this delta M squared is delta M times M. Delta M squared is 2M delta M. So I have M over E, okay? And this is T. So if we actually move to so this T, I should write it as tau, right? Is the time in the rest frame, is the self-timing, okay? So basically, neutrino oscillation, you just take the neutrino oscillation in the rest frame and you boost it. And when you boost it, you get the M over E factor, okay? It's the same story. It's really the same story. Good. So we understood this. And now we actually know what how to treat these things. So all I need, in order to find A of T, in order to find this oscillation and to understand what I'm doing, what I really need, I need to understand my Hamiltonian of the system, and then I can move on. So let's try to discuss a little bit the Hamiltonian of the system. Okay? And see what we have. So it's a cool system because it's a 2x2 Hamiltonian, because I assume that I have only a B and a B bar. So therefore my Hamiltonian is a two-dimensional Hamiltonian. However, that's something very important here. My full Hamiltonian is not 2x2. Why my full Hamiltonian is not 2x2? Because the B meson can decay. And also everything that the B meson can decay is also part of my full Hamiltonian, right? My full Hamiltonian is a B bar, a D muon neutrino, D electron neutrino, D star mu, etc., etc. All the things that the B can decay for. So my full Hamiltonian is kind of an infinite matrix Hamiltonian, right? Here I have a B, here I have a B bar, and here I start having whatever. D pi, dk, etc. All the things that we decay to, okay? And then we use the following thing that we say, oh, I want to use, instead of the full Hamiltonian, I want to use just the effective Hamiltonian. I want to use only this part of the Hamiltonian. Have you seen it before? That you take your Hilbert space and truncate it? Right? You've seen it before. For example, coming back to the hydrogen atom, when you treat the hyperfine splitting, that's what we did. We forget about the n equal 2 and n equal 3. Right? We only use the n equal 1 solution for the hydrogen atom when we treat it. What we do, we truncate our Hamiltonian. Okay? It's the standard thing that we do in physics, and that we use scale separation, right? So here we want to do the same. We say we neglect part of the Hamiltonian. What happens when we use only part of the Hamiltonian? What we are losing, what the basic property of the Hamiltonian is the Hamiltonian is Hermitian, right? When we treat only part of it, this is not Hermitian Hamiltonian. And in general, well, we call it also an open system. An open system is a system where the Hamiltonian is not Hermitian. Okay? And an open system is a system where the probability is not conserved. Right? We call it a decay. Right? A decay is when the probability is not conserved. So if I have a B meson, the probability to find the B meson is not 1 because you have a decay. Why? Because I treat it as an open system. Okay. We all know this kind of things. So now we write my Hamiltonian. I therefore write my Hamiltonian as M minus over I to gamma, such M is the Hermitian part of the Hamiltonian, and gamma is the non-Hermitian part of the Hamiltonian. actually it's the anti-Hermitian part of the Hamiltonian. Okay, so M and gamma are both Hermitian, but because I have the I here, this becomes anti-Hermitian when I put it into the Hamiltonian. And we have a very intuitive feeling of what it is. This is just the mass term, and this is the decay. Make sense? Very good. So now, there's actually, I know a few more things about this Hamiltonian that are very specific to these things. So the first question I want to ask you, what can you tell me about H11 minus H22? Okay? So I'm writing my Hamiltonian now as a 2 by 2 matrix where this is a B and a B bar, a B and a B bar. So what can you tell me about H11 and H22? Proportion to the mass squared. So I'm working in this basis. Of course, the basis choice, right? So I want to emphasize, I work in this basis. That's B and B bar. That's my basis choice. What I can say about H11 and H22? They must be equal. Everybody? They must be equal. Why? If something is equal, the answer is because of a symmetry, right? Good. Which symmetry? CPT. What CPT tells us is that the particle and an antiparticle must have the same mass and the same width, right? So CPT guarantee that H11 is equal to H22, okay? So now my general Hamiltonian will be H11, H11, and here I have M12 minus I gamma 12, and here I have M12 minus I gamma 12 star, and they are the same. So because they are Hermitian, right? So this matrix is not Hermitian, you see, because it's minus I in both sides. If it was Hermitian, it will be plus. Okay? So just look at this matrix and you say, oh, what is this H11? To leading order H11 is the mass of the B and the decay width of the B, which is of order, we know it, right? 5 to 80 for the mass, right? What is M12? M12, what is where this M12 would come from? It would come from the box diagram, right? And this is much, much, much smaller than this one, okay? So what kind of a matrix we have? We have a matrix where we have very, very big elements in the diagonal and very, very small elements in the off-diagonal, okay? So now what is the angle the diagonal? Let's forget about gamma for a minute. Let's assume that gamma goes to 0. What would be the angle that diagonalizes this matrix? Almost, kind of, no. What is the angle that, these 2 by 2 matrices, we should know them. We should really know 2 by 2 matrices. 45 degree. Why 45 degree? Because this is the generate. And you really have to remember this formula. Tangent 2 theta is this over the difference, right? And since the difference is 0, tangent 2 theta diverge, and therefore it's 45 degree. It's always like this. When you have a matrix where the 2 diagonal elements are the same, the rotation, the angle of rotation is 45 degree. You feel it? I really hope you feel it, right? Not yet. Play with 2 by 2 matrices. I mean, it's you really have to know those. You have to feel it. You have to feel it, right? I mean, there's some feeling for 2 by 2 matrices. Like you look at them and, right, stare at them. Particularly when you cannot fall asleep. Immediately look at 2 by 2 Hamiltonians. Boom, right? That's what happened to me last night when I start preparing the lectures. I looked at this and boom. That's why I couldn't come to hike this morning, because I didn't finish preparing last time. Okay, so basically you have a 45 degree. So now it's become a little bit more interesting because this one is not Hermitian. And when you try to diagonalize this matrix, what you find out the following result. So I'm just telling you that I diagonalize this matrix. Why I want to diagonalize this matrix? Obviously because I want to find the mass eigenstate, and the mass eigenstate are what's going to give me the time evolution, right? So I diagonalize this mass eigenstate, and what I find at the end of the day, I find that my 2 mass eigenstates, which I call them B, L, and H, for the light and heavy mass eigenstate, are given by P of B plus minus q of b bar such that p squared plus q squared equal to 1. Okay, that's just a solution. Just take this matrix and diagonalize it, and I find that that's my general solution. Okay? And P and Q are given by some M12 and gamma 12. Okay? I'm not going to give you what they are. They are related to M12 and gamma 12. The big point is as following. In general, P and Q are not equal. Okay? P are not equal to Q. All I'm telling you is that P squared plus Q squared is equal to 1. But I don't tell you that P is equal to 1 over square root of 2. P and Q can be different. And since P and Q can be different, what is the following matrix element? BL and BH. What is this equal to? So this is equal to, I just plug it into here, and I find that this is equal to P squared minus Q squared. Okay? And in general, it doesn't have to be 0. And now my question, you should be like so surprised.
P and Q are real numbers.
P and Q are not real. They are actually, they have a phase, and this phase is unphysical, and some other things are physical, okay? And I don't have time to discuss what are physical. I have so much more. Unlike previous lectures, I was completely off with what I thought I will be covering. So now the question is, what does it mean that you have two mass eigenstates that are not orthogonal to each other? Right? We learn, again, since we were kids, right? I remember in kindergarten that the teacher discussed orthogonality of wave functions. You remember this? Right? Said, eigenvalues of the eigenfunction of the Hamiltonian are orthogonal. You remember this? We were sitting like on the ground, and the teacher was... And then boom. What does it mean that I have my eigenvalue of my Hamiltonian are not orthogonal? Think about it, you have a two... Because it's not Hermitian. So what does it mean really about thinking about time evolution of non-Hermitian mass eigenstate, or in particular not orthogonal mass eigenstate? What does it mean? So if I produce my mass eigenstate, I can still measure it as the other mass eigenstate because they are not orthogonal. Right? Usually in our regular pictures is that if I have a muon, then there's no way it is an electron because they are orthogonal mass eigenstate. But here this is not the case. If I produce a B heavy, there's still some probability that I measure the other mass eigenstate at the same situation. That's this result of the fact that it's not Hermitian. And actually, one can show, and as I say, unfortunately I'm running out of time, one can show that this happened only if we have CP violation. So one condition for CP violation is that if they are not orthogonal, we must have CP violation. P, the absolute value of P, not equal to absolute value of Q, is a result of CP violation. In other way, if I impose CP, CP will give me the absolute value of P equal to the absolute value of Q. Okay? And that's somewhat the meaning of that CP is not conserved. And if CP is conserved, then BL and B heavy are eigenvalues of CP. Okay? However, when CP is violated, they are not, and in fact, they can kind of mix into each other. So we actually understand this kind of oscillation, and we understand that this oscillation is not as trivial as the oscillation that we have just when we have just mass and Hermitian Hamiltonians. The non-hermeticity of the Hamiltonian and CP violation can give me this kind of interesting effect. And this interesting effect, at the end of the day, we can actually use to measure these kind of things. So before I finish, I completely will not have time to cover CP violation at all. But I want to finish just with one thing. So when we do this calculation of Meson mixing, we define two parameters that go under the amazing name of x, which is delta m over gamma, and y, which is delta gamma over 2 gamma. And these parameters are the important parameters that give us the relevant time scales. And we talk so much about the importance of time scale in oscillation. So let's only consider x for now. So when x is very, very small, what you can say about the oscillation? When x is very, very small, when x goes to 0, how important oscillation are? Not at all, right? Because the particle basically has no time to oscillate, right? What happens in the other limit when x goes to infinity? Then it oscillates very fast and we average it out. Remember we talked about Quark's oscillation, that the x go to infinity limit, right? If delta m is very, very large, it just oscillates so fast, and we don't care about it, we average it out. And then, of course, we have the case that x is approximately 1, and that's very interesting because then you actually can measure delta m, right? When x is small, you cannot measure it. When x is large, you cannot measure it because it's averaged out. When x is of order 1, we can actually measure delta m, okay? And then we went out, and it took, 40 years, and we measure x and y for all the four mesons that we have, okay? And the result is as following. So that's x and y, and here I do k, d, b, and b sub s, and the answer is as following. For k, both x and y are of order 1. For d, they are both order 10 to the minus 2. For b, it's order 1, and that's order 10 to the minus 2. And for b sub s, that's order 10, and that's order 10 to the minus 1. And that's a very surprising result, because delta m comes from the box diagram that we calculate, and lambda comes from the decay, this tree diagram decay. They are sensitive to different masses, to different mixing angle, for different anything. And there's absolutely no reason for x to be roughly 1. And what we find that the four mesons that we have in nature, very big surprise, all of them are really close to 1. This one is 0.97. This one is 0.73. Very, very, very close to 1 for absolutely no reason. This is whatever, 10 to the minus 2, and this is actually, this 10 is more like 25. Okay? But still, all of them are within 2 orders of magnitude of 1. So while in principle we could have been really unlucky and x would be very, very far away from 1 and will not be able to do anything, it's just experimentally a miracle that actually all of them are at the region that we can actually start doing very interesting experiments with them. So unfortunately, I ran out of time. I had like so much more prepared. So actually, I could have gone to hike anyway, right? Because I didn't cover all this. So that was twice a mistake. But we could actually go and think. And I want to talk about how you measure CP violation and using this kind of things. Question? Delta gamma is the difference between the two lifetime of the two states. So when I diagonalize my Hamiltonian, I get my two mass eigenstates. And these two mass eigenstates, each of them has its own mass and its own lifetime. And delta gamma is a lifetime difference. And the K-on system is very significant. That's why you call it K short and K long. In the other system, this is is not very important. For the B sub s, it's surprisingly also kind of important. Okay.
Why is it important in terms of observing?
So what's happened? Think about the K-ons. So the K-on, because K long have so much longer lifetime, what's happened is the oscillation die out and you get only one mass eigenstate. So you have oscillation if both of them are there. One of them decay and the other cannot decay, you don't have oscillation, you just have a decay afterwards, right?
Right, but you can already observe it with just fact that x is not 1.
Oh, yeah. I mean, I'm just saying that in general, the general formalism is you care about x and y. And in K-ons, they are roughly the same. For the D, it seems we didn't really know, but it seems that actually y is much larger than x, much larger by a factor of 3. Okay, and actually that's the most important thing. You can actually do it. It's just that's what the formalism gives us. Okay, so let me conclude what I was trying to say today. So what I was trying to get to you today is the fact that the whole subfield of how we do these measurements, it's a whole subfield by itself, which is kind of decoupled from what I was talking to you the first three lectures. First three lecture was really model building, and here it's a whole different story. The question is, how can we actually get around QCD? And there's many, many tricks, and I cover only very, very few of them. And that's a big field of trying to get them. And the interesting fact is that we are roughly where the experiments are. That is, in some cases, our theoretical tools are better than what the experiments are doing right now, and in some cases, experiments are better where we are. And that's a very interesting kind of combination, is how can we actually come with either theoretical ideas or better ways to do calculation that we can actually get around QCD and get sensitivity to the weak scale. So eventually, we can kind of use it for model building. So that's it for me. Thanks.